All right, welcome to lesson 5.5, Advanced Algebra Notes, Performing Function Operations. Uh, as you can see, we've got kind of one big idea here. It involves multiple things. Our operations are our four big operations: add, subtract, multiply, and divide. And then the second part of the lesson really just kind of involves what happens with once we add, subtract, multiply, or divide a couple of functions. What happens to the domain? Do they get blended together? Is it is it unique? So that's basically what we'll look at. So kind of like a summary piece here that we'll start with, and then here's really the main notes, and then we'll look at some examples. So hopefully we can keep it manageable. Let's see, let's do it, let's get it going. So we spent time in class going over just some functions that we should be familiar with. Some of the properties looked at, like what does a graph look like, some examples of linear power, and then these root functions. um, so we'll do the same here. We don't need to spend forever with it. Hopefully there's things here that we should recognize. So we kind of just listed, like, what are some examples of linear functions using numbers and just actual examples. So stuff like, um, your traditional 2x plus 5, something like that. That's an example of a linear function. All right, I got a slope of 2, y-intercept of 5. That's kind of your classic example. There's variations, right? We could see things where all you have is a slope, is y-intercept is 0, or even just a y-intercept, y equals 5. Those are all examples of linear functions, lines. If we were to graph them, we would see they all take on some. We won't graph. I won't. We don't even need to be super accurate here. The graph of a linear function is a line, right? It's the root word there, linear. So the reason we're looking at this here mainly is to review domains. I'm assuming for a lot of us, that's probably the spot of this lesson that we're gonna just need the most work with. And so the domain of every linear function we're going to say is all real numbers. Remember, domain is looking at the left and right of the graph. What are the left inputs? How far left does this graph go, or what's the smallest x value that you could plug in here and still get an output? Well, there is no limit, right? We can go to the left forever. So what we'll use using interval notation here, we'll say all real numbers using this notation, saying we can go to the left forever. Negative infinity would be the furthest left on the graph, and then the graph also indicates that we can go to the right forever, right? This is forever moving to the right. So this is our way of identifying and saying the domain of all linear functions is all real numbers, negative infinity to infinity. Okay. Let's move on to power functions. Let's try to section this off, keep it somewhat followable here. So power functions are anything that involves an exponent that's a whole number. So a positive whole, nice counting number, other than 1 and other than 0. So something, let's keep it simple, 2x squared. I don't know why I go with 2. I like 2 as a coefficient for some reason, apparently. 2 or negative 2. 2x squared, and there could be others that follow, right? Plus 7x minus 3. Our quadratic functions are a perfect example of what we would call a power function. And as long as I keep the exponent as a whole number, negative 7x to the third power. So we'll throw our cubic functions in there, right? There could be a bunch of other stuff that follows that, but that would be an example of a cubic. So I think that hopefully it makes sense there, is we're looking for decent, good numbers as far as our exponents. I feel like I got more space with that linear one. I don't know. Graphically, these are all going to be different graphs, but we should know that our quadratic graphs all took on a parabola shape, or our our cubic graphs all took on that unique shape there, where it was, kind of that bend, it flattened out a little bit, almost like a parabola that was half of it was reflected over the x-axis type of thing. But I guess long story short here, when I start talking about domain and we start talking left and right, both, whether I'm talking parabola or anything in between, right? Even higher level, 4th degree graphs we saw did stuff like this. They had the little bumps in the middle, but it still went left, left, left forever, and then right, right, right forever. So for any power function, we're seeing domains of all real numbers again. So far so good. Hopefully that makes sense. Nothing too crazy out of the ordinary. I feel like I should have did odd root first. Maybe we will. Maybe we'll jump down there. So if you're making your notes at home with me, let's do odd root here. We'll come back and hit even root, because odd root we're coming off of lessons, some of the previous 5, 1, 2, and 3 stuff. 5, 4. We were looking at odd roots. Y equals the cube root of 2x. There's my 2 again. Couldn't be a function if I didn't use a 2. Just joking there. But so we got a cube root of 2x. The fifth root, y equals 5 times the fifth root of x, something like that. So anything that involves an odd root, the one that's maybe not as recognizable might be something like this: y equals 4x to the 2/3 power. So that one is definitely kind of tricky, because it looks, I mean, it looks like a power function almost, because it's got an exponent. But we should know from the previous sections that that could be rewritten and viewed as the x squared to the cube root of x squared. All right, if I wanted to rewrite this here, y equals 4 times the cube root of x squared. So there's different stuff going on there with that, but I have the cube root involved. So maybe I'll take this last part off just because it's getting kind of tight there. But so those are just some examples of stuff that we've been working with cube roots. Graphically, we should recall this from not too long ago, that you're basically your parent cube root graph takes on a shape here. They're all going to kind of have that similar quality. It's almost like our cubic graph turned on its side, rotated. So for the third straight time, when I start talking domain, as far as what x values are going to give us an output, we say that's fine. We can cube root, we can fifth root, any number we can think of. So and the graph kind of gives it away, saying we can go to the left forever, we can go to the right forever, no issues. All right, so 3 of the 4 functions that we're going to work with in this lesson all involve all real numbers, negative infinity to infinity. The one standout, the one weird one, is what we kind of save for the end here. I should have wrote it, and I kind of left myself a little bit of room there. Is our even roots. So what's the deal here? We'll write them underneath it so we can hopefully save a little room. So stuff like just real basic, the parent function, y equals the square root of x, right? There's a 2 there as an index that we're not seeing. Let's get a pointer there before you erase everything, right? There's a 2 in there, so that's an example of an even root. Something like y equals, let's do kind of that disguised one, that 5x to the 3/4 power. That's a good one. Again, it looks that's a little harder to tell as an even root, but that 4 as a denominator in the exponent makes that an even root function. Or anything with an even root. So y equals the 4th root of 5x. Oh, there's a 5x. So those are examples of even roots. Hopefully we recognize those. Graphically, we're going to see hopefully something very different. Here's our parent function. Let's graph y equals the square root of x. Remember, those ones had a clear, like, what we would call maybe starting point, where this graph was 0, 0 was like the furthest left this graph went on that parent function. Why? Because it's restricted. We're not in the real number system. There is no square root of negative numbers. Right? If I tried to plug in a -2 here, I would get in my calculator and I tried to calculate it using my calculator, it would say error, domain error. So that's why, like, our graph, everything else we've talked about goes left, right forever. This one didn't go left forever. It went right forever. So we have what we would call like a restricted domain. And if we can fit it in here and make it all look nice and neat. So usually, at least on the parent function, our domain, unless there's a horizontal shift, which we saw, so I shouldn't say usually, but anytime there's nothing being added or subtracted directly to my x and not taking us left or right, we were 0 to infinity. Okay, left was 0. 0 is okay. You could plug 0 into any one of these and still get an output, but anything left of 0 is no good. Right is fine. So yeah, maybe a little bit longer than I said I was going to do, but it's a good summary, mainly looking at those domains. So a lot of all real numbers. The one we got to be on the kind of lookout for is even root functions. All right, so kind of just put a pin in that for right now. We'll come back to them in a second. Let's get our operation, right? That's the name of the lesson, operations on functions. Let's get those notes hammered out here. So we did this, we added this in class. Basically saying, we'll I'll try to summarize it here. So we've got any two functions, f and g. We'll work with these four types that we just talked about, linear, power, because even within power, you have multiple different types. There's quadratic, there's cubic, there's quartic, there's different ones in there, and then even in odd root ones kind of hold a few different types. So we're working with a few different types of functions. We can build or create a new function by combining the original two together. So I think this is a pretty okay illustration. I was going to say decent. It's not bad. They're both linear. We're combining this 5x function with this x plus 2 function. They're both linear. Basically what it says, if we add those, part of this is notation, getting familiar and comfortable with seeing f plus g in parentheses of x. What does that mean? Like that's saying take this function and add it to this function. So take the 5x, add it to the x plus 2, and actually combine anything that you can combine to simplify it, 6x plus 2. Okay, and that follows with subtraction, multiplication, division. You can see them on here, f minus g of x. That's how we would say that. F times g of x would look, if you look at them individually, f times g of x, f over g of x, f of x divided by g of x. In the simplification is going to vary. So like here, notice we're going to distribute. We would let's see if I can get the pen up here, just to kind of make sure we don't miss any of this stuff. This minus is going to get distributed there and there. So 5 minus x, that's where the 4x came from. But then notice the 2 became negative. If we were multiplying these two functions together, this is what the notation would look like, what it would tell us to do. So I'd say, okay, let's take the 5x and multiply it by that. So it's a distributive situation, 5x squared, and then there's where the 10x is coming from. And then last one is division. Not a whole ton of simplifying on that one, really none, just other than taking f of x and putting it over g of x. Okay, so that's how that would simplify. So that's the performing operation part of it. The second part of the lesson is what's going on with the domains. Okay, so this is the book, how the book says it. The domains of sum, difference, product, and quotient consist of the x values in the domains of both f and g. Additionally, the domain of the quotient does not include x values for which g of x equals 0. Okay. Here's my takeaway. This is the Mr. Kroll spin on it. Basically, any restrictions on any of the individual function at the start is going to be on the final domain. So that's why this one's not the best illustration, because if I look at this 5x, what's the domain of that 5x? Well, it's all real numbers. It's negative infinity to infinity. And then same thing here with this other linear function. We're talking negative infinity to infinity. There are no restrictions. So these results have no, like the 6x plus 2 has no restrictions. This 4x minus 2 has no restrictions. This 5x squared has no restrictions. The one part that we do have to watch out for is, which is my last part that you should add to your notes, when we divide with division, the one operation we got to look out for is we got to look at that denominator and think about, is there anything included here? So if I were just to say, hey, you know what, this new function here, this 5x over x plus 2, that domain is all real numbers because the original two were all real numbers, so that's just what we're going to use. I've got an issue on my hands. There is one number in here that's included from any number that you could think of. What number could I plug in here that would give me an error that either my calculator couldn't compute or is just undefined? And it says it right here with division, we can't divide by 0. So 0 is okay to plug in here. 0 over 2, if I plugged in a 0, 5 times 0 is 0. 0 plus 2 is 2. 0 over 2 is 0. The number that's going to rule us out here, are going to make a bad situation, an undoable situation, is -2. And let's just make sure we understand why. If I plug in a -2 up top, what do I get? I get -10. No problem. But if I plug in a negative, I would also need to plug in a -2 downstairs in the denominator, which is going to create a 0. And if we tried to on the calculator, or just from what we should know about dividing by 0, we can't do that. It's not defined. Okay, so long story short, use any restrictions here. If there's no restrictions, well, for addition, subtraction, multiplication, there won't be any restrictions. With division, we can kind of lean on that to start, but then I just got to look and see. There's probably at least going to be one number that's going to say, yeah, that bottom, we got to take that out of that solution set. So we could write it just like this: -infinity to infinity, other than x can't equal -2. All right, so hopefully that makes sense. If not, we'll look at basically I've got, what do I got? 4 is kind of just an addition, subtraction, multiplication, division example. We'll look at a word problem situation that isn't much more. It's an addition, subtraction type of one. And that's what we got. Let's do it. All right, here we go. Example 1. We got 2 different functions. I see let f of x equals 3 times, or equal 3 times the square root of x, and then let g of x equal -10 times the square root of x. Find f plus g of x. Let's just stop there. All right, that's one task that it's asking us to do. All right, find f plus g of x. So the interpretation there is, and I'd like you to use the notation. Like, let's get familiar with using this function notation. What is f plus g of x? It's equal to adding the 2 functions together. So taking 3 times the square root of x and adding it to g of x, -10 times the square root of x. Okay, so we got everything kind of where they go, and then we'd look at it and say, all right, well, can we simplify this? And yes, we should. We need to simplify this. We don't want to leave multiple square roots going on in the same problem, or multiple x bases. So hopefully we recall from previous lessons. I would say 5.2 is where you should refer to if you're looking for notes on this. This 3, this 10 get combined as almost as like as coefficients. They are coefficients. What is 3 plus -10? -7. And then the square root of x is just along for the ride. Okay, so that's the first part. When it was asking us just to find f plus g of x, we did it. Not bad, right? The simplifying can be tougher. Like that, I'm not saying that's like the end all be all. That's the hardest one we'll ever do, but we did it. We combined those, -7 times the square root of x. And then state the domain of this. Now, here's where I got to be careful. I think I should have maybe did this to start. The easiest thing that I've kind of found over the years of doing this is just right off the bat, initially on these 2 original functions, identify the domain. What is the domain of this 3 times the square root of x? And right off the bat, I guess we're seeing one that's a 0 to infinity. That this is an even root function, right? It's a square root graph or square root function. And then I look at this one, and I say, what's the domain of -10 times the square root of x? Well, that is also an even root function, so that has a 0 to infinity domain. So what we just talked about, the kind of nice part here is, if these are both the same, 0 to infinity, 0 to infinity, and we're either adding, subtracting, or multiplying, which we were adding, there's almost like no thought involved. I don't want to say that because we did put some thought into it, but I'm just going to use the domain, like it wouldn't change. It's going to be 0 to infinity, 0 to infinity. So my resulting one is also going to be 0 to infinity. Okay, all x is greater than or equal to 0. Cool, that's the second part. We've identified the new one's domain. State the domain. The last part is now saying, all right, then evaluate the sum, so this original sum, when x equals 4. Another just kind of cool part, instead of going all the way back to the beginning and saying, all right, well, I got to plug in a 4 here, I got to plug in a 4 here, we can use this one that we came up with. We did the sum already. Why do it all again? Just, again, watch your notation here. So we would say f plus g, not of x anymore, but of 4, which is what we're plugging into this function, equals negative 7 times the square root of 4, which is going to be 2. So ultimately, the calculation we're going to do is negative 7 times 2, which is negative 14. Okay, so we get to use, our result. What was the result of performing this operation? What was the domain of that? And then use it, on just kind of an example of plugging a number into it. Watching the notation, keeping track of what we're doing. You can use capital D for domain. All right, and they all kind of follow that same process where you're going to find 3 different things. Do the operation, what is the domain of it, and then input an X value. All right. Okay, let's keep it moving. Let's do a subtraction. Different functions, and obviously, like I didn't say this here, but it's good. The difficulty can vary. These are now power functions. Okay, so I'm going to do some of that stuff. I think it's just good practice to right off the bat look at my 2 functions. F of x is this cubic function, 3x to the third minus 2x squared plus 5. What is the domain of that? Well, if I check back on my summary page that we started with, that's a power function. That's all real numbers, negative infinity to infinity. Okay, let's look at g of x. G of x is another cubic function, another power function. So that's great. We like that. Those are nice ones. Those are ones that have negative infinity, all real number domains. Because later on now, I could, without even seeing the result of this, what we're going to do here is subtraction, without even seeing the result, I can guarantee you that the domain is going to be negative infinity to infinity, or all real numbers, without even seeing the result. So that's kind of cool. Just take care of the work early on here and then deal with it later. If it was division, I would probably wait and see on my result. But for right now, it's subtraction, so I think that's what our domain is going to be. Let's do the subtraction part of it first. I always try to go in order then. So f minus g of x, again, the interpretation is saying leave the x in there, but just take f of x, which is 3. I'm going to try to slim it down here a little bit on my handwriting, try to skinny it up because I think I'm going to have a tough time fitting it all in, plus 5. So f of x, 3x to the third minus 2x squared plus 5. And then we're going to subtract, right? That's what it's telling us to do. Subtract this whole function. So be careful here. Use parentheses. I would encourage parentheses here. Why? What's the big deal? Well, we've done stuff early when we added and subtracted polynomials, and that's essentially what we're doing right now. We're subtracting 2 polynomials. So with subtraction, the deal was to remember that, and we can do it right on here, that this subtraction right here, it needs to get distributed to all the pieces along the way. So it's actually minus x to the third power plus 3x squared minus 4x plus 2. So the sign on every single one of these ends up getting switched. And if I do that, now I can treat it like addition and just combine all my like terms. So we can get our result here, our resulting function, our new one. Let's see, what do I have to combine here? This 3x to the third minus my x to the third, so 2x cubed. Whoops, almost wrote squared. Cubed, I'm going to kind of just take them out of there so I don't lose them. What do we got? A negative 2x plus 3x, or squared. So negative 2x squared plus 3x squared is positive just 1x squared. Let's see here. I do have one that's just kind of hanging out that I don't have anything to combine with, so minus 4x. Don't lose that one. And I think last but not least, 5 plus 2, 7. So positive 7 on that. Oops, positive 7 is where we end up as a result. F minus g of x, there's our result, another cubic function. All right, so that's part 1. Find f minus g of x, done. State the domain. Let's get that knocked out. We said from the get-go that the domain, just if they're both the same, our domain is going to stay the same. We got kind of 2 in a row like that. We'll see some other ones. We'll see some wrinkles here going forward that it doesn't always work that way. So great, that's awesome. All real numbers. And then the last part, what's it asking us to do to plug in a negative 2? Let's see here. Can we squeeze in an f minus g of -2 equals. So I'm going to come below a little bit here just so I can, so I'm going to plug in a -2 here, here, and here. So we're going to go 2 times, let's see, -2 cubed plus, use parentheses on your substitution. I know we've done this quite a bit this year. We're making graphs and everything, but forgot my calculator here, so I'm going to do my best to get this knocked out. What do we got? The first one would be -8 times 2, which is -16. We're going to add that to +4. And then we're going to add another 8 onto that, and then 7 onto that. What are we talking here? 7, 15, 19, and then minus 16.3. So I got 3. I hope that's all right. If I screw it up, I'll come back and edit at some point. But I think we're okay with 3 there as I'm doing that in my head as I'm talking right now. So f minus g of -2 ends up being 3. Use your calculator. Don't do what I'm doing here. Use your calculator. All right. So again, same deal. There's my composition, or not my operation, my domain, and then using it to plug in a number. All right, let's keep her moving. We're getting there. Slow and steady. All right, a multiplication. This is a good one here for us. Okay, we'll see a couple different new pieces. I think the functions themselves on the initial here are slightly simpler, right? We got an x squared and a square root of x. But what are we being asked to do? We're being asked to multiply them, state the domain, and then evaluate. So same deal. All right, so domain-wise, can we do it here? Let's see. This is a power function. This is a quadratic. That is in all real numbers, -infinity to infinity. But this next one, if I can get an arrow there maybe, that's a square root graph. That's an even root. That is one that has a 0 to infinity domain. We can't square root negative numbers, right? Go check your notes. We did it in that even root section. So we have those there. We'll come back to the, let's just hold on to that until we get to the domain part of it. The other thing I think about this one that's going to be helpful, well, let's see here. Let's just see what happens. So if it's asking us to do f times g of x, it's basically saying take f of x, which is x squared, and multiply that by g of x, which is the square root of x. So I get here and I see, man, it feels like we should simplify this, but I honestly, I don't know how. X squared times the square root of x. What does that mean? There's x's here and here. So I think on this particular one, it's kind of a mismatch of forms here. I don't like, one of them has an exponent, one of them has a square root. We can help ourselves out in the simplification part on this. If I change, and again, we're recalling stuff from previous sections, that, oh yeah, the square root of x is the exact same thing as x to the 1/2 power. And so we've seen this same base being multiplied. What do we do with their powers or with their exponents? We'd add them up. Okay, yep, that's right. So you could look at getting a common denominator here. You could rewrite this as x to the 4/2 times x to the 1/2 power, and say that when this is all said and done, f of g, or f times g of x, is x to the 5/2 power. All right, so a little bit different there, right? Where we had kind of that mismatch of forms, but we were able to kind of move it around a little bit and simplify it to a nice just single base x to the 5/2 power. All right, domain-wise here. When it comes to a mismatch of domains, so we kind of got a mismatch on another level, you're always going to pick the most restricted, right? We said that was part of our notes. I just want to make sure we didn't miss that. Any restrictions on an individual originally will be on the final. So that's kind of a fancy way of saying use the one that has the most restrictions. Well, this one's unrestricted. That's all real numbers. This one's only 0 and above. So this one's restricted. We want to use this one. My resulting domain should be 0 to infinity. Okay. So that's a new piece for us. Use the most restricted. And then the last part, same as before. Let's do our substitution, our plug-in. F times G of 9 is going to be, let's just use this one right here. All right, so 9 to the 5 halves power. Uh-oh, we're going to test it here. I should probably just get a calculator. Give me a second here. I know it's going to be 3 to the 5th power. I just don't want to screw it up. 3 to the 5th power. So I did the square root of 9, which is 3. And then 3 to the 5th power, I think it's 243. Yep, ran and grabbed my calculator. 243. Just wanted to make sure if I'm making video notes, I should probably make sure the solutions are correct, right? All right, so we plugged in the 9 there, got our 243. All right, let's do a division one. Division's the most to think about. It's probably the toughest one. Another good look here with a mismatch of domains. So this one should be good for us. Last one. Or last, I guess, traditional, and then we'll look at that example 5. So following our process, identify your domains initially. This 6x, that's linear, right? Unrestricted, negative infinity to infinity, all real numbers. This is kind of that tricky one. This one actually, I think, came up in our review summary page. The x to the 3/4 power is somewhat disguised there, but that is an even root function. That 4 as a denominator is like a 4th root. So that's one that we got to say, hey, no negative numbers allowed here. Only 0 and above. So the other thing to notice is, what are we being asked to do? It says find f divided by g. Okay, division. I'm going to hold off on writing my domain answer until I can see what's going on here, okay? So let's start there. F over g, or f divided by g of x, is going to be taking f of x, which is 6x, and dividing it by g of x, which is x to the 3/4 power. Can that be simplified? Yeah, I think so. Kind of like the last one, we have x's and x's in the same problem. We can fix this. So the question would be, where do I have more x's? What's the exponent on this top x here? I don't see it. It's 1, right? So you could maybe help yourself out a little bit. Switch that 1, instead of writing it as x to the 1st power, but writing it as x to the 4/4. That's 1. A strategic one, because now we're going to be able to subtract. So where do I have more x's? In my top, in my numerator. And how many more? Well, 4 minus 3 is 1, so 1/4. So this simplifies all the way down to 6x to the 1/4 power. All right, so we've done that part. That can be tricky. I know I'm going quick on that. I'm kind of counting on us to be able to do some of that stuff from previous lessons. All right, state the domain. Tough. First time seeing it here. So what did we just say on the last one? When it's mismatched like this, there's a negative infinity to infinity and a 0 to infinity. So I'm kind of taking this one off the table. We're already restricted here. We're going to use this one. But let's look. Are there any numbers in this from numbers from 0 to infinity, which is a lot? Oh my gosh, we got to think about all those numbers. Well, no, not really. We just got to think, what number in this denominator, even going back to the very original, what number would create a 0 ignoring, let's see, can we do this? Can it be tricky? Ignoring the numerator. What number would you have to plug in for x and take it to the 3/4 power to get 0? Because 0 is the bad guy in the bottom here. We don't want a 0 downstairs. So I run through and say, well, let's see, 0 to the 4th power, to the 3/4 power is 0. So that would create a 0 in the denominator. It would also create a 0 upstairs, but even 0 divided by 0 is still undefined. So long story short, 0 is no longer okay. 0 is not okay to plug in here. Even though on this one, if I just look at the end, it looks like, wow, 0 is fine. You can 4th root 0. But to get here, we had a few stops along the way. At some point, we would have put a 0 downstairs, which would have killed the problem, basically. Okay, so watch this. The subtle little change that happens from going from this, all numbers 0 to infinity, to this right here. what are you talking about, Mr. Crow? You just wrote the exact same thing. Not quite, right? What changed? We went from a bracket, bracket to a parenthesis and say, oh, big deal. So what? Well, what does that mean though? The bracket means zero is totally cool. You can plug in a zero. Parenthesis means zero is kind of the threshold. You can't use zero, but you can use anything bigger than zero. It's basically the difference from going from x has to be greater than or equal to zero to x has to be greater than zero. That's exactly what that means. Here, greater than or equal to zero applies. Here, x has to be greater than zero. So that's going to take practice, looking at your denominators and seeing what value is going to make that, and then taking it out of your domain. All right, we can still, though, for the last part, when it's asking us to do to evaluate f divided by g of 16, I can still use this one up here. I don't have to go back to the beginning of the problem or anything like that. So 6 times, I just felt like I was missing something there, times 16 to the 1/4 power. Let's see. That's 6 times 2. Is that it? 12? I think we're all right. So there we have it. That's, for the most part, that is the lesson. That's doing the different operations, kind of a 3-part problem. I think all the assigned problems that I'll have you practice follow that exact same process. Kind of getting comfortable with the notation, simplifying, using the notation for the domain, and then using that a little bit. Let's look at just I think a relatively, I hate to use simple, but it's addition example. It's power functions. It's something that is fairly relatable. I think the numbers, the setup is all something that I hope kind of makes sense. So let's talk through it here. Where like I always get the question, where are we going to use this? Where would we see this? So at least here's a somewhat real life problem that we might see something like this. Okay. All right, from 1990 to 2010, the number in millions, so we're talking huge numbers here, of female and male employees from the ages of 16 to 19 in the United States can be modeled by, and then we get 2 models. So F, it's telling us, is for female, M is for male, ages 16 to 19 in the US. So this top function right here, F, I know the decimals and negatives and it's craziness, f of t equals negative 0.007 t squared. That represents the number of years since. So the t is the number of years since 1990. So for example, if I were to plug in a 5 for t and do all this stuff, square it times this times point, and the result, what would that result be? That would be the total number in millions of female employees ages 16 to 19 in the US. In what year? We said a 5 we were plugging in. 5 years from 1990 would be 1995. So I just kind of randomly picked 5, but that's the example of what you would be plugging in there. Same thing for this lower one. It's just for male employees. So if I plugged in a 10 here for T, I could figure out, oh, okay, cube it, square it. There's my 10. In the year 2000, how many male employees were there in the United States ages 16 to 19? All right, so just kind of breaking that apart a little bit. I get it. That's kind of intimidating, seeing all these big decimal numbers and this M and T and so I get it. Ultimately, what are we being asked to do with this information? Okay, so if I look, part A is saying it was our very first example we did here. I'm going to kind of work, and I'll probably have to scroll up and down. Find f plus m of t, right? We were doing stuff like f plus g of x. This is no different. It's telling us to add these 2 functions together. Take this f function and add it to this function right here. That's it. Cool. And they're both, like I said, both power functions, so it's going to end up ultimately being in combined like terms. I'll break them apart a little bit here. I'll probably have to come down and squeeze my writing a little bit. So let's start with the female model. We've got negative point. I'm going to take that first 0 off there. 0, 0, 7 t squared. I'm just copying it down. Plus 0.10 t plus 0.37, or I'm sorry, 3.7. Okay. And we're going to add that to, I'll change colors here, the male model. So 0.0001 t to the third power minus 0.009 t squared plus, are we going to get it in here? 0.11 t plus 3.7. Oh, we just fit it. Right? Notice I didn't use parentheses like the subtraction one because essentially the plus would just get carried over and go plus negative 0.09 plus 0.112 plus 3.7. So it really wouldn't change anything. You could do it. And I'm not saying it's a bad thing to do. So the last part here, can we do this one? I get the calculator out. I think we'll be okay though. Let's see. I saw a cubed in there somewhere. So there's nothing to combine with this one. We're talking, if I'm writing this, if I'm doing the simplification now, 0.000, I feel like I got so many zeros in there, but that's what it says. All right, t to the third power. Let's see. We're going negative 0.007 minus, so that should be negative 0.016 t squared. I think, again, I'm not reaching for the calculator, but I think 7 plus 9 is 16 and slide our decimal over, or slide it over 1. Okay. Plus, right here, 0.1, 0.11, so 0.21 t. And then 6, 7.4 plus 7.4. We did it. I mean, other than working with the decimals, which use your calculator, that wasn't bad. Okay, so add the two functions together. That's what it told us to do. Where people kind of get stuck is they don't even realize what this is asking you to do. You know, so just I'll flip back. But if I look here, right, this one, I covered it up, but it did ask us to do that. It said add the two functions together. I know I kind of talked through it, and we're used to maybe lowercase letters or whatever it is, but I've seen people get to this one and they're just like, I don't know what this is asking me to do. Like I don't get that. So it's just add the two functions together. All right. Last part B, last note here for the day. What does this represent? What is, when we did that, explain what f plus m of t represents. What is this right here? A bunch of decimal numbers smashed together. Who cares? No, like going back to the context, that's why I spent a little bit of time talking through it. What did we just do? We added the model that gave us the number of female employees ages 16 to 19 in the US. We added it with the male model of, again, the same thing that tells us the number of male employees ages 16 to 19 in the US, T years from 1990. When we add those together, what is that going to give us? The total number, male and female together, employees in the U.S. age 16 to 19, T years after 1990. So it's kind of a mouthful. Let's write it out though, and hopefully that, like I said, that makes sense. That when we found this new model right here, instead of doing it individually by gender, we look at and say, well, you know what? I don't care about male, female. I just want to know total. How many employees were there in the U.S. age 16 to 19, X amount or T amount of years from 1990. So let's say that. What does it represent? F plus M of T represents, let's use a sentence here, represents the total number of employees ages 16 to 19 in the U.S. There's a bunch of kind of just a bunch of tags on it, right? It's ages 16 to 19 in the U.S. T years from 1990. All right, so I hope that makes sense. So now that we have kind of this new model, if that's all you wanted to know, instead of doing two separate calculations here and here, let's just do one. Plug in, how many employees were there in the year 1991? Plug in a 1 there, and and there, and that's what it'll tell us, the total number of employees. Okay. So that's our last example. Look at that. Not terrible. I feel like we've done longer. We've hit them all. Add, subtract. We did basically one of each. So I mean, obviously, we got to practice a little bit more than that. We did add, subtract, multiply, divide. Looked at their domains. We even attached to a word problem to it. Plugged in some numbers there. So we did it. 5.5 in the books. Done. Over. I will see you in future lessons.